So, welcome to this class on hardware security. Today, we shall be discussing on a topic which is called as field isomorphisms, which is a very important mathematical tool to develop efficient architectures for finite fields, which we can apply for realizing efficient architectures for subsequently for AES kind of ciphers. So, the concepts that I shall be trying to cover in today's class, or I shall be starting to cover in today's class, is we shall take a recap on groups, rings and fields. We shall be discussing about binary finite fields. We shall be discussing about a concept which is called as primitive elements, and then define what are called as bases of fields, and then finally discuss about isomorphisms and composite fields and try to construct isomorphisms. So, to start with, here is a quick recap on what are called as mathematical groups. So, as we know that mathematical groups are defined by an operator or a binary operator, say denoted as dot, such that if I take any two ordered pairs A and B which belongs to G, then the following axioms holds. The first is closure, that means if I take two elements A and B in G, apply the operator, then the result is also in the group. It is associative, which means I can do either A dot B dot C, where I can do either B dot C first, or if I do A dot B first, the results are same. Okay, so that is, you can do it in any way. The third property is identity element, which means that there must be a unique element E which belongs also to the group, such that if I take A, which is another element in the group, and then I apply the identity element either on the right or on the left, I still get back the original element, which is A. That means A dot E is equal to E dot A, which is equal to A for all A which belongs to G. Likewise, you also need to have an inverse element, which means that for any element A which belongs to G, there must be an element A dash which also belongs to G, such that A dot A dash is equal to A dash dot A, which is equal to the identity element. If the group also satisfies commutativity, which means that I can do A dot B or B dot A for all A B which belongs to G, then it is called as a commutative group, or often called as a abelian group. So, you can extend a group to a ring by bringing in another operator along with the. So, now you have got two operators, say plus and dot. Often the first plus is called as the addition, and the second one is thought to be like something like a multiplication or product. So, such that so again, like few axioms have to hold. For example, for all ABC now which belongs to R, that is the ring, the following properties hold. The first is that R has to be an abelian group under addition. Then with respect to multiplication or the dot operator, the closure property of R has to be satisfied. The associativity property of R is also satisfied under multiplication. There exists a multiplicative identity element denoted by 1, such that for all A which belongs to R, again I can do A dot 1 or 1 dot A, I get back again I get back A. Okay. There is another law which also needs to be satisfied, which is called as a distributive law, which means like now if I have got three elements which belongs to R, then A dot B plus C essentially is equal to A dot B plus A dot C, which means multiplication distributes over addition. Likewise, you can also do A plus B dot C, and you will have A dot C plus B dot C. So, therefore, there are several examples of rings. For example, the set of integers, real numbers, rational numbers, complex numbers are all examples of rings. So, a ring is also again like in a similar way, like in the groups, is said to be commutative if the commutative property under multiplication holds. That means for all A B which belongs to R, we have got A dot B is equal to B dot A. So, therefore, it is called it is an example of a commutative ring. Then we have got something which is called as field. So, a field is denoted as F plus dot, again you have got two operators, and so it's called a field. So, we extend the concept of groups to rings and then rings to fields. So, what is a field? So, field is a commutative ring which satisfies the following conditions. So, it of course satisfies the properties of what are called as commutative ring, as we have seen in the previous slide, but we extend it with some more conditions. For example, if you remember in the last definition, we did not say that every element must have a multiplicative inverse. So, now we bring in that notion where we say that for all elements A which belongs to F except 0, that means for all non-zero elements of A of F, there exists a unique element A inverse such that A into A inverse is equal to A inverse into A is equal to the multiplicative identity or 1. Now, the multiplicative inverse is denoted as A to the power of minus 1. So, essentially it says that all non-zero elements have multiplicative inverses, and it also has got no zero divisors, which means that if I have got elements A and B which belongs to F, and if I have got the result A dot B equal to 0, then either A is equal to 0 or B equal to 0, which means that two non-zero elements in the field should not multiply to get 0. This is an important condition for it to be a field. So, the set of rational numbers, real numbers and complex numbers you can easily understand are now not examples of are examples of fields, but the set of integers is not an example of field. Why? Because multiplicative inverse property will now not hold. You can easily see that suppose 5 is an integer, and if I say like 1 by 5 is an inverse of it, for example, but 1 by 5 is not an integer. Okay. So, therefore, it does not have a multiplicative inverse in the set of integers. There is another very important notion which we already have kind of discussed in the previous classes, which is called as characteristic of a field. Now, what is a characteristic? Now, it is a minimal value of the integer k such that if I take an element A, for example, and if I add A say k times, I get k dot A which is equal to 0. So, therefore, it is a minimum number of times I add an element A in the field to get 0 is called as the characteristic of the field. Now, you can easily understand that if it is a field and if A is a non-zero element, the A inverse also exists, and therefore, you can also synonymously say that it is the minimum number of times I add 1 to get 0. That means k into 1 is equal to 0. So, where 1 is of course the multiplicative identity of the field F. So, we have seen several examples of characteristic P fields, characteristic 2 fields. So, in particular, as we have discussed previously, characteristic 2 fields are efficient because of the like the fact that it gives rise to like compact and efficient architectures. So, in GF2, which is essentially the smallest field in like in 0 1 domain, the elements are only 0 and 1. So, you have got either 0 and 1 as elements in this field, and it actually gives rise to very compact systems because most computing systems are built on binary number systems. So, it is very suited for our computing platforms. In particular, you can think about that a single bit can be used to represent an element in GF2, and for example, if you compare it with GF3, you will see that in GF3 you will have elements 0, 1 and 2, but you can easily think of that to realize these 3 elements you need 2 bits. So, therefore, you are basically having provision for 4 elements, but you are only using 3 elements. On the other hand, right, the utilization in GF2 is very compact because you have got a single bit to represent an element in GF2, and you know that you can have 2 elements represented in GF2 and you have exactly 2 elements in GF2. So, therefore, you are not wasting any storage or wasting any space. So, therefore, GF2 seems to be very efficient, and indeed as we have discussed previously as well that there are the operations, for example, addition is very easy in GF2, there is no carry. Okay, so, the addition in GF2 can be realized by only XOR or exclusive OR, and also like you can also extend GF2 to something which is called as an extension field, which is denoted as GF2 power of m, which also leads to efficient arithmetic operations, like as we have seen squarings and inverses and multiplications, which were pretty efficiently implemented. So, therefore, this brings us to this concept of binary finite fields. So, a binary finite field can be represented as a polynomial Ax, where I have got say like the degree as x power of m, so the degree is m till say a constant term A0, such that all the coefficients here are belonging to GF2, which means they are either 0 or they are either 1. So, furthermore, this polynomial is said to be irreducible over GF2 if Ax is divisible by C or by C dot Ax. That means, so where C is of course like a constant which belongs to GF2. So, that means you do not have any non-trivial factors of the polynomial which belongs to this field. So, an irreducible polynomial of degree m with coefficient in GF2. So, now if you have got such an irreducible, suppose this polynomial is irreducible, which means like you cannot have such kind of trivial factors. So, you cannot have trivial factors for this polynomial Ax. So, then it qualifies as an irreducible polynomial. So, what you do is you take the ring of polynomials, that means all polynomials possible in GF2x. That means all, essentially simply put, it just means that I will take all possible polynomials whose coefficients are in GF2, okay, and then I will divide it, or rather I will take the remainder after I divide that polynomial with this irreducible polynomial. So, you can easily understand that if the degree of this polynomial is m, then the degree of the remainder will be maximum m minus 1. So, therefore, write any remainder that I get, or any modulo that I get, any modulo polynomial that I get, have got a maximum degree of m minus 1. So, therefore, the number of elements which I need to represent that moduli is ranging from 0 to m minus 1. So, there are m bits, and you essentially have got 2 to the power of m such possibilities. So, that means like you can represent all elements in GF2 to the power of m using that representation. So, essentially this particular extension is what is called as an extension field. All elements of the extension field therefore can be represented by a polynomial of degree m minus 1 over GF2, and this way we construct the extension field GF2 to the power of m. So, now let us see an example. So, in particular I shall be constructing this field GF2 to the power of 4, which is an extension of GF2. So, the irreducible polynomial that I use for this purpose is x to the power of 4 plus x plus 1. Note that there can be more than one irreducible polynomial, and I just choose one of them. So, I choose an element which is called as a generator x, which is also, like you can think of the definition of a generator by being an element in the field, which if you raise to its powers, it can actually generate all the non-zero elements in the field. Okay. So, note that it is not, you cannot generate 0 out of this, okay. You can generate all the non-zero elements from x. So, what I do is I calculate x, x power of 1, x power of 2, x power of 3, and so on till x power of 15 to get back 1. So, after x power of 15, I will again get x, and the process and the pattern will repeat. So, basically what I have done is that in GF2 to the power of 4, there are 15 non-zero elements, that is one element which is 0, but all these 15 non-zero elements can be now generated by only x, and by reducing it by x power of 4 plus x plus 1 whenever the degree exceeds 4. So, let us see the process. Suppose I start with x, I then calculate x squared, then I calculate x cube, okay, and then when I calculate x power of 4, as I said, I have to reduce this. So, how do I reduce it? I substitute this x power of 4 plus x plus 1 as 0, which means x power of 4 is equivalent to x plus 1. So, therefore, I replace x power of 4 by x plus 1. Then I again multiply this with x, so I get x squared plus x, and then I get x cube plus x squared, then I get x power of 4 plus x squared. X power of 4 is again replaced by x plus 1, so I get x squared plus x plus 1. And if I repeat this process in this fashion, you will see that finally in the 15th position I will get x to the power of 4 plus x, which is nothing but 1. So, therefore, the process will repeat after this, and again I will have x, x squared, x cube, and so on. Okay. So, therefore, this x or this polynomial x serves as the generator, and as we shall see subsequently, this is also called as the primitive element in this field. Okay. So, that essentially brings us to the primitive element of the field. So, in general, if you in a more general setting, if you consider the field GF2 to the power of n, there is an element alpha such that for every non-zero element, can be written in the form of alpha power of k. This element is called the generator or the primitive element on the group. Now, there is a concept of a special class of polynomial which is called as the primitive polynomial. So, what is a primitive polynomial? A primitive polynomial is a monic polynomial of minimum degree such that the primitive element is a root of the polynomial. This primitive element that we have been talking about is a root of this polynomial. So, it is the minimum degree polynomial or minimum degree monic polynomial where the primitive element is a root. Interestingly, a primitive element is always irreducible, but not vice versa. Over GF 2 to the power of n, there are phi 2 to the power of n minus 1 by n, where phi is the Euler-Troschen function, number of primitive polynomials possible. So, there are more than one primitive polynomials possible, whose essentially, which means that if I take these polynomials and I equate to 0, then I will get elements which belong to the extension field and are roots of those polynomials. So, those elements which are roots, or those roots essentially are primitive elements of this field. Okay. So, with this background, right, we essentially can start to look into the fields in much more like in much more details. So, how do we express the elements in the field? There are two important ways in which you can do that actually. Okay. One is what is called as polynomial basis, and the other one is what are called as normal basis. So, in polynomial basis, you again start with an irreducible polynomial. Again, as we have been discussing, that if I want to extend GF2 to GF2 power of m, then I have to use an irreducible polynomial. So, let's suppose like Px is an irreducible polynomial, and let alpha be the root of Px. Okay. So, in particular, right, what I will do is that I will then generate or rather I will write my polynomial base as 1 alpha, alpha square, so on till alpha to the power of m minus 1. So, this becomes the what is called as a polynomial basis, which means I can express any element in this field using linear combinations of these components. Likewise, there is also a normal basis, which is essentially again starting from Px, which is an irreducible polynomial over GF2 to the power of m, and let again alpha be the root of Px, then the set alpha, alpha square, alpha to the power of 2 to the power of 2, likewise alpha to the power of 2 to the power of m minus 1. Okay. Again, you will see that you have the same number of elements in the basis. Okay. So, this sequence is what is called as a normal basis if these m elements are linearly independent. So, if this m, there is an important criteria where the m elements have to be linearly independent. So, again you can express any element in the field also by linear combinations of these bases. Okay. So, there are important ramifications between them, between the polynomial basis, which probably is more simple to explain, and the normal basis, through which you can actually have very interesting constructions, very efficient constructions. So, both are useful, but let us try to look into the polynomial representation. So, in the polynomial representation, any element in the field can be expressed in terms of its basis. The basis is, as I said in the previous slide, where I have got 1 alpha till alpha to the power of m minus 1. So, if I want to express say any element, say GF2 to the power of m, so this should be GF2 to the power of m, an element can be expressed with respect to its polynomial basis as a alpha. So, you can see that I am now having a general representation which is Ax, but I have now taken a specific instance of that. Okay. So, how I am generating this element? I am taking linear combinations of my basis elements. So, the coefficients of my linear expansion essentially are denoted as A0, A1, so on till A minus 1, and these elements can be either they are in GF2, that means they can be either 0 or they can be either 1. So, therefore, you can easily understand that this particular representation essentially can cover all the can cover the entire field GF2 to the power of m. So, it can very much represent any element in GF2 to the power of m. Okay, and that is why these particular choices are essentially gives you the basis. Okay. Note that you cannot express alpha power of m minus 1 by the other components. Okay, that means these are the minimum number of elements which are required to express all elements in the field. Okay, in the field. So, now we are in a position to understand this concept of isomorphisms. Okay. So, what are isomorphisms? So, suppose you have got two groups G1 and G2, and I want to define a surjective function G1 to G2, that means from G1 to G2, such that the following condition holds. So, what is the condition? So, I have got an operator here. So, suppose this operator is denoted as circle. Okay. So, that means I do circle operation between elements in the group G1, and I do an operation which is defined by a dagger symbol on the group G2. Okay. So, therefore, right, if I want to do an operation between x and y and calculate x circle y, I can also do this alternatively by mapping both x and y to this target group G2 by applying the mapping f, for example. So, therefore, now I get f x and I get f y, and then I apply the dagger operation between f x and f y. So, I get f x dagger f y. So, therefore, here we were like we took x, we took y, we applied the operator circle and got x circle y. So, now if I apply the function f to the result, I get f x dagger f y, and it turns out that f x dagger f y should be same as calculating f x of f x dagger f y should be the same as f applied on x circle y. Okay. So, then this particular function is said to be a homomorphism. Okay. So, it is said to be homomorphism if and only if f x circle y is equal to f x dagger f y. Note that the operators on the left and the right need not be the same. Okay. They can be same, they may not be same. So, when I further qualify this mapping as an injective function, that means it is a one-to-one function. So, it is a one-to-one homomorphism, then this is what is called as isomorphism. Okay. Now, the idea of the isomorphism can be extended from groups to rings and fields. In this extension, the only difference is that you have got further two operations rather than one operation. So, therefore, right, you have got, suppose your operators are plus and dot, then we say that the mapping from R1 to R2 is a field isomorphism if and only if f of a plus b is equal to f of a plus f of b, and f of a dot b is equal to f of a dot f of b. Okay. So, I have just tacitly assumed that the operators are same on both sides, but you can also generalize that. So, therefore, this happens for every a and b which belongs to R1. Okay. So, this essentially gives us the definition of isomorphism. So, let us try to see whether we can understand isomorphism in more details by taking an example. So, again I will take up my example of GF to the power of 4, and again I have represented all the elements in GF to the power of 4. So, now note that now I have got also 0 which is over there. So, I have got all the 16 elements. So, there is one which is 0 and then there are 15 non-zero elements in the field. So, now as I said that there are 3 irreducible polynomials of degree 4 which can be used to construct these above field elements. The first one, as we have seen, is z to the power of 4 plus z plus 1. You also have got another candidate f2z, which is z to the power of 4 plus z cube plus 1. And then there is a third one which is called as f3z, which is actually a pentanomial. So, these are examples of trinomials, but now you have got another polynomial which is a pentanomial, which is z to the power of 4 plus z cube plus z square plus z plus 1, which is also an example of an irreducible polynomial for GF to the power of 4. So, therefore, what I do is I extend using f1z, the field is what I call as say capital F1. I extend again GF2 to GF2 to the power of 4 by using f2z, and that field I called as capital F2. Likewise, I have got capital F3. So, now you can easily understand that all the resulting fields will have 16 elements. Interestingly, the operations will be different. For example, like if I want to do say z into z cube, in the first field I will get z to the power of 4 will is the result, which is equal to z plus 1. In the second field, however, that result will be z cube plus 1. Okay. And in the third field, it will be z cube plus z square plus z plus 1. So, you see I am doing the same operation, but I am getting different results, okay, because the fields are equivalent, but they are not equal. Okay. So, now I can actually like establish isomorphism between these fields. I can say that like all these fields are actually equal, but they are equivalent, but we can actually establish some kind of relationships between them. So, the fields are isomorphic and we can establish a mapping between say F1 and F2, and I will try to show you that how we can establish this mapping. Okay. So, first what I do is this: I start computing an element C which belongs to F2, such that if I take the irreducible polynomial F1, which is the irreducible polynomial of the first field, and then substitute C in that, okay, then you can easily understand that what I will try to do is that I will try to calculate this modulo of F2. Okay. And if I calculate modulo of F2 and then I get 0, then what I will say is that my Z is mapped into C. Okay. So, what is Z? You can easily understand Z will satisfy F1 in the first field, okay, but not C. So, what I am trying to do now is that because C is an element in F2, so if they are equivalent, then C should satisfy F1, but modulo of F2, okay, and this trick will work. So, let us see. So, how we can like develop an mapping using this observation. For example, suppose I take C is equal to Z square plus Z. Okay. So, to verify, what I do is that I calculate F1 Z square plus Z. So, F1 Z square plus Z is, so if you remember what is F1? F1 is Z to the power of 4 plus Z plus 1. Okay. So, therefore, right, if I substitute Z as by Z square plus Z, so I get the result as Z square plus Z whole to the power of 4 plus Z square plus Z plus 1. Okay. And that if you expand, I will get Z to the power of 8 plus Z to the power of 4. Remember that 2 is 0 in this field, plus Z square plus Z plus 1 modulo of F2. And what is F2? F2 is Z to the power of 4 plus Z cube plus 1. So, I can substitute Z to the power of 4 by Z cube plus 1. So, therefore, Z to the power of 4 is Z cube plus 1, and likewise Z to the power of 5 is Z to the power of 4 plus Z. If I replace Z to the power of 4 with Z cube plus 1, then I get Z cube plus Z plus 1, and likewise Z to the power of 6 is, again if I multiply this by Z, I get Z to the power of 4 plus Z squared plus Z, and again I will replace Z to the power of 4, I will get therefore Z cube plus Z squared plus Z plus 1. So, note that Z, again I can get Z to the power of 8 by directly squaring this. So, I get that as equal to Z to the power of 6 plus 1, and I replace Z to the power of 6 by this expansion. So, I get Z cube plus Z square plus Z. So, then F1C modulo of F2 is nothing but, as we have seen, Z to the power of 8 plus Z to the power of 4 plus Z square plus Z plus 1, and that, but that becomes equal to 0. Okay. So, you can easily see this, that if I like combine Z cube plus Z square plus Z with Z to the power of 4, which is Z cube plus 1, okay, then I will get and add Z with it, and add 1 with it, and add Z square with it, then the elements will get cancelled and I will get 0 modulo of F2. So, let us check on the homomorphism property. Okay. So, in the homomorphism property, you consider two elements E1 and E2. So, suppose E1 is equal to Z square plus Z, and E2 is equal to Z cube plus Z. Okay. So, these are two elements in F1. So, therefore, if I want to do the product in the field F1, that is simple. I will take Z square plus Z, multiply it with Z cube plus Z. So, I will get Z power of 5 plus Z power of 4 plus Z power of 3 plus Z square. So, in the field F1, I know Z to the power of 4 is Z plus 1, and Z to the power of 5 is Z square plus Z. So, if I substitute this, then the product, right, becomes Z square plus Z plus Z cube plus Z plus 1 plus Z square. Okay. And that becomes equal to Z cube plus 1. So, I get the result as Z cube plus 1. So, now let us see the, like if I apply the homomorphism property, I get the same result. Now, the same operation can also be performed in the field F2. What I do is I apply therefore this mapping on E1. So, what is the mapping? I will replace Z by Z square plus Z. Okay. So, what is E1? Z square plus Z. So, therefore, I will replace this Z by Z square plus Z. So, I get Z square plus Z whole square plus Z square plus Z, and then I do a mod of Z to the power of 4 plus Z cube plus 1, because that is my field polynomial in F2. So, therefore, if we expand this, you will get Z to the power of 4 plus Z square plus Z, which is equal, and then I do a modulo of this, I will get Z cube plus Z plus 1. Okay. Likewise, I do TE2, which is again this element. So, now again I replace Z by Z square plus Z, I do a similar manipulation and I get Z plus 1. So, now if I take these two elements, then they are elements in F2 now, because I map them to F2, I apply multiplication in them. So, I take Z plus 1, multiply it with Z cube plus Z plus 1, do a mod of Z to the power of 4 plus Z cube plus 1, and this result is equal to Z square. So, let us check this result whether indeed satisfies the homomorphism requirements. Okay. So, if you remember, like what we have got in the previous computation was we got the result essentially in the field F1, and the question is, right, we would like to see that when we so the field the result in field F1 was Z cube plus 1, and if we transform this result into the field F2, I should get the same result as that I get when I multiply the elements TE1 and TE2. Okay. So, in T1 and T2 I get the result as essentially z square. So, therefore, now if I map z cube plus 1, I should get z square. So, let us verify that. So, if I want to map z cube plus 1, therefore, my process is I will again replace z by z square plus z. So, I will calculate z square plus z whole cube plus 1, and therefore, if I expand this, I will get z to the power of 6 plus z to the power of 5 plus z to the power of 4 plus z cube plus 1. And then remember, in this field F2 I will do mod of z power of 4 plus z cube plus 1. So, therefore, if I replace this term by term, you can verify that the result is indeed equal to z square. Okay. So, therefore, it indeed satisfies the property of homomorphism. Okay. So, let me stop here. So, we shall continue from this point in the next class, where we shall try to understand how we can construct these transformations or homomorphisms or isomorphisms in a more algorithmic fashion. Okay. Thank you.